Some plastics left out in the sun for a few months crack, fade, or crumble into dust. Others, amazingly, seem to repair themselves or remain nearly unchanged for years. Why does sunlight destroy certain polymers but leaves others intact or even helps them self-heal? This strange difference is known as the UV degradation paradox, and it reveals just how complex and clever modern materials science has become. At the center of this puzzle is ultraviolet UV light, a high-energy form of light in sunlight that is invisible to the human eye. UV photons carry enough energy to break chemical bonds, especially the carbon-carbon and carbon-hydrogen bonds that form the backbone of most plastics. When a polymer absorbs UV light, its molecules can become excited, leading to bond scission, the breaking of chains, and the formation of free radicals, highly reactive fragments that go on to attack other parts of the material. Over time, this damage accumulates. The result? Fading color, brittleness, cracks, and complete breakdown. But if UV light is so destructive, how can any plastic resist it, let alone heal from it? The key lies in the chemical design of the polymer. Some polymers include UV-absorbing additives called UV stabilizers that soak up damaging rays before they reach the main molecular chains. Others are engineered to have aromatic rings, which spread out and absorb the energy safely without breaking. But in the last 2 decades, researchers have gone even further. They've created self-healing polymers that actually use the energy from UV light to repair themselves. That sounds impossible. How can light that normally breaks things be used to fix them? The answer involves special bonds and smart chemistry. Some self-healing materials contain reversible bonds, such as Diels-Alder linkages or disulfide bridges, which can break and reform under specific triggers. When UV light is applied, these bonds can be temporarily broken, allowing the molecules to move and rearrange. Then, when the light is removed or the temperature changes slightly, the bonds reform, healing the material. In some systems, UV triggers a small flow of polymer chains that move into cracks and seal them before further damage occurs.
Can we see this in action?
Yes. Researchers have developed coatings for cars and electronics that self-heal minor scratches when exposed to sunlight. One example involves a polyurethane with special fluorinated side chains that soften and move slightly under UV light, sealing over damage. Another material developed for aerospace uses light to trigger a localized chemical reaction that fills microscopic cracks, preventing them from spreading into larger fractures. Meanwhile, everyday materials like polyethylene or polystyrene lack these smart features. They absorb UV light and degrade quickly, especially if they're thin or exposed on rooftops, roadsides, or playgrounds. Over time, these materials contribute to microplastic pollution as they break into ever smaller pieces. This environmental challenge has pushed engineers to design UV-resistant bioplastics and photodegradable polymers that break down under sunlight on purpose, turning UV from a threat into a recycling tool. So the paradox is clear. Sunlight can be both a destroyer and a healer. Whether a polymer degrades or repairs depends not on the sun, but on how the material is built. Scientists now design polymers at the molecular level, choosing bonds that either survive UV exposure, block it, or harness it for useful functions. It's a shift from seeing light as damaged to seeing it as energy and using it in new adaptive ways. Would you like a diagram showing how self-healing and degrading polymers differ in their bond structures? When UV photons are absorbed by polymer chains, they can excite electrons in specific chemical bonds, leading to homolytic cleavage and the formation of free radicals. These radicals propagate via chain scission reactions, reducing molecular weight and degrading mechanical properties. Oxygen can react with these radicals to produce peroxy species that further accelerate breakdown through oxidative pathways. The rate of scission depends on the polymer's absorption spectrum and bond dissociation energies. Without protective measures, this process continues until the material embrittles and fails. Polypropylene exposed to sunlight for weeks becomes brittle and cracks as UV-induced scission shortens its chains. It is like cutting a rope, one link at a time, until it can no longer bear any weight. UV exposure often leads to photooxidation, where free radicals react with atmospheric oxygen to form carbonyl and hydroperoxide groups, known as chromophores. These new groups absorb visible light, causing yellowing and loss of transparency in plastics like polystyrene. Chromophore formation also creates stress concentration points that nucleate cracks under mechanical load. The accumulation of oxidized moieties thus both weakens and discolors the polymer. Controlling oxygen diffusion and radical concentration is key to mitigating these effects. Clear polystyrene food containers turn yellow and become brittle after prolonged outdoor storage. It's like leaving a white shirt in the sun until it acquires permanent yellow stains. UV stabilizers, such as hinderedamine light stabilizers and UV absorbers, work by scavenging free radicals or dissipating absorbed energy as heat. Hales preferentially react with polymer radicals to form stable nitroxyl radicals, interrupting the degradation cycle without being consumed rapidly. UV absorbers, like benzotriazoles, absorb high-energy photons and de-excite safely, preventing bond cleavage. The choice and concentration of these additives determine the polymer's resistance to photodegradation. Without these stabilizers, even inherently robust polymers degrade under sunlight. PVC roofing membranes containing UV absorbers retain strength and color far longer than unstabilized samples. It's like wearing sunscreen and antioxidants to protect your skin from sunburn and cellular damage. Some advanced polymers incorporate reversible bonds, such as Diels-Alder adducts or hydrogen bonds, that break under UV stress but reform when the light source is removed or upon mild heating. These dynamic bonds enable microcracks to close and restore mechanical integrity through spontaneous bond reformation. Embedding microcapsules of healing agents can also release monomers that polymerize upon UV damage. The efficiency of healing depends on bond kinetics, network mobility, and catalyst presence. Such designs mimic biological repair by balancing bond breakage and reformation under environmental stimuli. A Diels-Alder-based polyurethane coating exposed to UV can recover 90% of its original toughness after a gentle heat treatment. It is like a zipper that unfastens under stress, but zips itself back up when you pull it again. Highly cross-linked polymers resist UV-induced chain scission because their network restricts radical diffusion and redistributes stress across multiple bonds. However, limited chain mobility can also hinder self-healing processes that require segmental motion to reform bonds. Conversely, lightly cross-linked or linear polymers allow greater mobility but suffer faster degradation without network reinforcement. Optimizing cross-link density is thus a trade-off between durability and repairability. Tailoring network architecture through co-monomer selection and cross-linker type controls this balance. Cross-linked epoxy resins maintain shape and strength under UV better than linear polyethylene, but cannot self-heal microcracks. It's like choosing between a rigid fortress that never shifts and a flexible tent that can be patched but is less protective. The intrinsic chemical structure, such as aromatic rings, unsaturated bonds, or heteroatoms, governs a polymer's UV absorption and radical formation propensity. Polymers with conjugated backbones like polycarbonate absorb more UV and require robust stabilizers, whereas saturated backbones like polyethylene absorb little light but still degrade via secondary oxidation. Fillers like titanium dioxide scatter UV light, providing passive protection. Antioxidants intercept peroxy radicals before they attack the backbone. A synergistic suite of additives thus tailors photostability for specific applications. Outdoor paints often include both UV absorbers and titanium dioxide to reflect UV and prevent binder degradation. It is like layering a tinted window film, a reflective coating, and a shade to protect interiors from sun damage. Real-world degradation involves not only UV, but also temperature fluctuations, moisture, and mechanical stress that synergize to accelerate breakdown. Cyclic heating and cooling cause thermal expansion and contraction, opening microvoids that allow oxygen ingress. Rainwater and humidity can hydrolyze susceptible bonds, particularly in polyesters and nylons. Abrasion and windborne particles further expose fresh polymer surfaces to UV attack. An accurate understanding of service conditions is therefore crucial for predicting polymer lifespan. Outdoor automotive bumpers fade and crack faster in desert climates, combining intense UV heat and sand abrasion. It's like a rock face weathering faster in a desert storm than in a calm, shaded valley. Smart polymers embed photochromic or photocatalytic moieties that, upon UV absorption, trigger polymerization or cross-linking reactions that seal cracks. For instance, spiropyrin groups can generate reactive radicals under UV, initiating localized healing without external intervention. Other systems use titanium dioxide nanoparticles under UV to catalyze polymer bond formation at damaged sites. Efficient design requires spatial control of photoactivated species and oxygen management. Such materials offer autonomous repair capabilities in harsh sunlight. A clear coating with embedded spiropyrin molecules can self-seal scratches when exposed to midday sun. It is like a plant leaf that releases healing sap when its surface cells are wounded. Combining UV stabilizers, dynamic covalent bonds, and optimized network structures yields polymers that both resist breakdown and autonomously repair damage. Multi-layer systems can integrate a UV-bluing outer layer with an inner self-healing core. Molecular designs, such as incorporating low-energy dissociation bonds, controls where and how healing occurs. Accelerated aging tests under simulated sunlight guide formulation adjustments. This holistic approach drives next-generation materials for outdoor, biomedical, and space applications. A multi-layer roof membrane uses a UV absorber-rich surface and a healing underlayer that restores integrity after hail impact. It is like a fortified castle with a sun-shielding battlement above and a repair crew below that rebuilds walls overnight.